Good afternoon. It's an honor to be here with you today. We live in an era where the dominant scientific worldview is based on materialism, a metaphysics that holds aspects of this physical world, such as matter and energy, as self-existent. From the physical universe and its laws, this view claims we can explain everything we see and everything we experience. The material universe is sufficient to explain the nature of all that exists, and if that is true, then in the words of the late Stephen Hawking, science can explain the universe without the need for a creator. This, or some version of this view, is very common in our day, particularly in academic circles. Yet this view leaves many questions unanswered. For example, what is the nature of consciousness? What is the origin of morality? Does it even exist? What about love or mercy? Are these illusions? Are they simply electrochemical impulses? Did they simply arise as encoded reactionary patterns in our brains through evolution? If so, are moral principles simply reducible to mathematics and statistics? And finally, given these questions, can a proponent of materialism live their life consistently with their worldview? While these profound questions remain unanswered, materialists use ancillary arguments in support of their view. One such argument that I want to examine here is the appeal to mediocrity, sometimes called the Copernican principle. To explain what I mean, consider the story of the pale blue dot. In his book, The Pale Blue Dot, the late astronomer Carl Sagan recounts an event that occurred in the course of NASA's Voyager 1 mission. In 1990, 12 years after the launch of Voyager 1, the spacecraft had left the outer planets of the solar system, and on February 14th, it was commanded to turn around and take a family portrait of the planets in the solar system it was leaving forever behind. When the images were transmitted back, NASA scientists and engineers were having difficulty finding the Earth. Eventually they found it as a pale blue dot near a shaft of light that was entering the camera, reflecting from some point on the spacecraft. And about this picture, Carl Sagan had this to say: "Because of the reflection of sunlight, the Earth seems to be sitting in a beam of light as if there was some special significance to this small world. But it's just an accident of geometry and optics. Our posturings, our imagined self-importance, the illusion that we hold some privileged position in the universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark." As you can sense here, this is actually not a scientific statement, but a philosophical, actually a theological one. But the claim is not supported by all the science that we've learned over the last few hundred years, in fact. In this talk, I would like to examine the assertions of this so-called Copernican principle in the light of modern science, and in particularly my field, which is extrasolar planets or exoplanets. Before we discuss exoplanets, let's take a brief historical look. It was Aristotle who 2,400 years ago argued for a geocentric model of the universe. He envisaged a concentric set of crystalline spheres in which the heavenly bodies resided. Most nearby was the moon, then Venus, then Mercury, then Venus and Mars, and then Jupiter and Saturn. Further out were the firmament, which are the stars, and these were all set into motion by a prime mover. Aristotle said reason and common experience confirmed this view, and no one doubted it. But there was problems with this simple view. One was the retrograde motion of the planets. For example, if you look in the night sky, look at Mars, which comes near us every 2 years. It comes to a point called opposition, which is the point on the sky opposite to the direction of the sun at that time. And if you watch its location relative to the background stars, you would notice a retrograde motion. Over the course of a few months, you see the planet moving one direction, then backwards, and then forward again in the same direction relative to the stars. This was difficult to explain in the basic geocentric view of Aristotle. 500 years after Aristotle, in his great work called the Almagest, Ptolemy provided an explanation. He agreed with Aristotle that the perfect heavenly bodies have to have perfect motion, which meant they were going in circles. But the planets are actually traveling in smaller circles called epicycles, and the epicycles are centered on something he called deferents, which in turn are centered on the Earth. In this way, the planets can have retrograde motion. By setting the diameters and rotation rates just right, Ptolemy was able to make very accurate predictions of the locations of the planets, so good in fact, that for the next 14 centuries, there was no rival to this picture. It wasn't until the 16th century that a serious alternative was proposed. And here it was Nicholas Copernicus, who in his own magnificent work called On the Revolutions of the Heavenly Bodies, detailed a much more elegant system, the sun-centered or heliocentric system. The Earth, he suggested, was not the center of the universe, and the heavenly bodies do not all revolve around a central point. With these and few other axioms, he was able to explain the same observations more elegantly and simply. But it goes on further. In the 20th century, it was the astronomer Harlow Shapley of Harvard University who discovered that the sun is not at the center of our galaxy, which is called the Milky Way. He did this by measuring the locations of globular clusters on the sky, including their distances. Globular clusters are mini galaxies with hundreds of thousands of stars. Shapley noticed that they're orbiting an area of our galaxy that is many thousands of light years from us. So he famously concluded the solar system is off-center. That means we are off-center, and consequently man is too. So you see this pattern. Copernicus showed us that the Earth is not at the center of the solar system. Then Shapley showed us that the sun is not at the center of the galaxy. And later, though I didn't mention it earlier, Edwin Hubble discovered that the Milky Way is only one of hundreds of billions of galaxies. Pointing to these observations, this so-called Copernican principle seems to show us that man does not hold a central position in the universe. And by extension, it must be true that we are not here for a purpose. The claim seems to be well supported when I express it as I just did, but the claim gets some of the history wrong. For example, neither Copernicus nor Galileo would consider Earth's removal from the center a demotion. But also the claim actually completely misses much of what we've learned in the last century about habitable planets. These are planets where life could at least survive if placed there. So now we consider the question, what is a habitable planet? What do we need for a habitable planet? There are many requirements, but at a minimum, a habitable planet must be a terrestrial planet that supports complex carbon and water-based life. It needs to be a planet in what is called the circumstellar habitable zone. And finally, it needs to be a planetary system in the galactic habitable zone. The first requirement, mainly that it should be a terrestrial planet, meaning a rocky planet, is already limiting. This is because much of the matter in the universe consists of hydrogen and helium. It takes complex processes in the stars to generate the heavy elements that make up a planet that is rocky like the Earth. Beyond being rocky, however, it must also have water, and these are just minimum conditions. There is also the location of the planet. Their circumstellar habitable zone is defined as that region around the star where water could be liquid at some part of a rocky planet that is situated there. Since the surface heat of a planet is from the sunlight it absorbs. Around a cold star, the habitable zone is close in, while around a hot star, it has to be further out. If a planet is located closer to its host star than the inner edge of the habitable zone, a runaway greenhouse effect will raise its temperatures, causing the water to evaporate into the atmosphere and be carried away by the solar wind, making the planet dehydrated. At the other extreme of the habitable zone, there will be precipitation in terms of ice and snow, and that will make the planet absorb less of the starlight and become colder still. And this leads to an uninhabitable snowball planet. In our solar system, only the Earth is inside the habitable zone. So the planet has to be the right distance from the star. As for the star, are all stars equally suitable? It turns out the answer is no. Many astronomy textbooks refer to our sun as an average star. This is true only in a limited sense. There are certainly stars that are more hot than our star, and there are stars that are cooler than our star, than our sun. But the sun is actually within the 10% most massive stars in the Milky Way. And in fact, stars that are much more massive than the sun are actually too unstable to be producing habitable zones. And then stars that are less massive than our star have habitable zones that they're cooler, so they have habitable zones that are closer in, requiring that close, tight-in habitable zone. But then when a planet gets that close to a star, it suffers from an effect called tidal locking. So for the cool stars, the tidal locking problem occurs. The spin of the planet becomes equal in duration with its orbital period, and as a result, one side of the planet becomes permanently day, while the other side becomes permanently night. The day side becomes hot, and the moisture is transported to the other side, where it snows down and stays permanently frozen. Tidally locked planets are poor choices for life. Cool stars also have more frequent life-threatening events, these bursts called coronal mass ejections. In the end, only 4% of the stars are main sequence G stars, like our sun. And then what about the location of the star within the galaxy? To get heavy elements from which a rocky planet can form, you have to be closer to the center of the galaxy. On the other hand, if you get too close, life-threatening events like supernovae become more frequent. A supernova can sterilize life within many light years around it. These are more frequent not only near the center, but also within the spiral arms. So the planetary system, to stay safe, needs to be at the right radius from the center of the galaxy. Not too far, not too close, and not within a spiral arm. And what about the galaxy itself? Here too, we find ourselves in a privileged place. Our galaxy, the Milky Way, is among the 3% most massive galaxies in the nearby universe. Because it was so massive, it was able to accumulate heavy elements more quickly, and planet formation started here earlier in the Milky Way. Almost 2/3 of the age of the universe had gone by the time there was enough material that a planet like the Earth could be formed. So there was a brief window. There are, in fact, many parameters that we could discuss. The list is very long. Very briefly, at least we need a planet with a magnetosphere. Our magnetosphere on the Earth protects us from the cosmic rays and occasional solar bursts that would otherwise dehydrate our atmosphere. We need a large moon. The Earth's moon is unusually large relative to the Earth's size. This is important because our massive moon stabilizes the axial tilt of the Earth's rotation. And that helps to stabilize our climate. To support large living beings like animals and like us humans, a planet needs to have high enough oxygen content. But then if it has too much oxygen, there will be rapid fire growth. So there needs to be a neutral gas as well to avoid devastating fires. Our oxygen-nitrogen dominated atmosphere is perfect balance of these requirements. Finally, the Earth's planetary neighbors play important roles. Jupiter, the largest planet in our solar system, has 300 times the mass of the Earth. It has a near circular orbit and orbits 5 times farther from the Sun than the Earth. This combination of being massive and having a large circular orbit makes Jupiter a benevolent agent in the solar system, absorbing to itself, like a massive vacuum cleaner, comets and asteroids that could potentially threaten life on the Earth. Many of these eventually crash into Jupiter and Saturn. We now move from theory to experiment. Over the last 2 decades, there has been many discoveries of exoplanets, planets around other stars. What have we learned from them? First, very briefly, I'd like to point out some of the techniques. In the first very important technique called radial velocity, the planet is not detected directly, but the wobble of the star in reaction to the pull of the planet is detected from the red and blue shifts of the star's spectrum. Another highly successful technique called transit looks for the very small drop in the light from a star when a planet transits, when the planet comes in front of the star. A third one that is special to me, because this is the area in which I work, is one of direct imaging, where a technique is used to actually image the planetary system directly. Here you see a montage of many years of images of an exosystem and the planets going around that. Now, what have we learned from these? From the radial velocity measurements, we've discovered one important lesson, that Jupiters, like our Jupiter, are very uncommon. Most gas giant planets, and Jupiter and Saturn are examples of gas giant planets, have elliptical rather than circular orbits, it turns out. Over time, the elliptical orbit means they migrate towards the star, eventually settling from an elliptical orbit to a circular orbit very tightly around the star. Along the way, they can knock off other planets in the solar system. They are very dangerous when they do that. These kinds of planets are called hot Jupiters, and they're very dangerous. The other technique was the transit technique, and it has also provided us a picture of thousands of other planetary systems. But here too, the results show that in the great majority of the planets discovered, they are closer to their host star than even our innermost planet, Mercury. So our solar system, by that comparison, is exceedingly unusual. So we see a large number of conditions are necessary for a life-hospitable planet. And when we look at the universe, we see that the usual condition, the usual situation, is that these conditions are not all present at the same time. In fact, one can make a statistical estimate of the expected rate following the approach of Frank Drake from the 60s, where he used a very simple calculation, and he estimated the number of planets in the Milky Way that could host advanced life, such as could give us a radio signal. Considering a few conditions, he estimated that there should be on the order of a few million planetary systems in our galaxy that could send us a signal. But half a century later, the list of conditions are actually quite a bit more. And when you actually do the same type of calculation now, you expect much less than 1 in 10,000 Milky Ways where you could expect to see a planet like the Earth. So this isn't, up to now, has been an argument to say that the Earth is a very rare planet. But there is a yet more profound aspect to our existence here, and this is a notion of what is called the privileged planet. And this was first pointed out by astronomer Guillermo Gonzalez and philosopher Jay Richards. And their point was that the requirements for habitability appear to overall be coinciding with the requirements for discovery. That is, the same conditions that a planet should be habitable are altogether what we would need for that habitable planet to be a place where intelligent beings could study and learn about the universe. An example of this that is beautiful is the example of the perfect eclipse. Did you know that the Earth, from the Earth's point of view, the moon on the sky and the sun on the sky are exactly the same diameter? And as a result, the Earth is the only place where we can have what is called perfect eclipses. If the moon was a little bit closer, it would not cover enough of the sun. If it was a little bit farther, if it was a little closer, it would cover too much, and if it was a little farther, it would not cover enough of the sun. As it is, we have perfect eclipses, and we can study aspects of the sun that were otherwise unavailable to us. For example, historically, it was from observing the spectra of the atmosphere of the sun during a perfect eclipse that astronomers first discovered that the sun is a hot ball of gas. It also enabled them to know what elements are present in the sun. This in turn opened the door for studying other stars. It was also during an eclipse that Einstein's theory of gravity, which eventually told us about the beginning of the universe, was put to its most famous test. The sun's mass bends the light from distant stars, but the bending is so small that only stars seen very near the sun show an effect. But you can only see this effect during a perfect eclipse. Many of the other factors also facilitate discovery. But because we're not at the center of the galaxy, our night sky is dark. It's not bright. We can actually do astronomy. We also, remember, we said we need an oxygen-nitrogen atmosphere. Well, that's a clear atmosphere. By comparison, Venus has a carbon dioxide atmosphere, which is opaque. You couldn't do astronomy from Venus. It's also 400 degrees Celsius on the surface of Venus, so it's not a good platform. The list of interconnected requirements for habitability and discovery is long. But the picture by now should be clear. There is abundant solid evidence that the world is designed, and that we can infer as well that God wants us to study this world and to see its design and to realize the glory of its creator. So far from being a mere pale blue dot, our planet is not only made for supporting life, but it was also made to support